Okay, guys, we will talk about thermal stress and thermal strain. And before that, we need to revisit the concept of elongation. Elongation. So, elongation generally occurs if there is deformation or deformation. Deformation is elongation due to the force applied on a bar or a body. If there is a uniform cross section. Okay, so pardon my figure, and force P is applied, then we know that stress is E, which is modulus of elasticity, Young's modulus times E. This is our strain. So we know that this stress is P upon A. E is there, and del L by L. Okay. So if we rearrange this, we get that dl equals to pl upon ae. This is the formula of elongation for a uniform cross section. What is this? Uniform cross section. Now, what if there is a not uniform cross section, taper type cross section, like this? This is d1, this is d2, this is l, this is p force applied here. So in that case, our elongation formula will be, remember this, 4 times pl by pi e d1 d2, 4pl by pi e d1 d2. And what if there is a elongation due to self weight of the material? That is, okay, self weight occurs like this. This is steel, and this is, okay, self weight is acting there. This is gravity that is acting there, and this creates self weight. So this elongation is quantified as del L. This, y is z times sigma. Okay. Okay. So it is not modulus of rigidity. It is z times sigma. Mm, I think this is all about elongation formula. Now we will talk about loading, triaxial loading. Triaxial loading means a body is loaded triaxially. There is a body. I'm making it sigma x y z, like we x y z. I don't know about the convention. This is my convention. So sigma x, sigma y, and sigma z. So in this case, strain in x direction, that is ex, equals to sigma x by e. Yeah, simple, minus mu times sigma y plus sigma z by e. In case of isotropic material, e are same in each direction, and sigma y and sigma z are loading in the other direction than x. This is x. Similar is the case on other three strain, sigma y and sigma z, e y and e z. Now volumetric strain. So what is volumetric strain? Ev is del b by v. We know this, but this can be quantified in terms of linear addition of ex, ey, and ez. Like this part for x, for y, and for z. So if we do like this, in terms of stress, sigma x plus sigma y plus sigma z by e 1 minus 2 mu. So this is a volumetric strain. Okay. Okay. What is this? Volumetric strain. Okay. Uh, Now we will talk about thermal stress. This is the main topic of the session. Thermal stress. There are different cases of thermal stress. We will look into four cases. First cases is free expansion. Free expansion. So in case of free expansion, rod is heated and it is allowed to expand as long as it wants. There is no constraint that is posed there. So we know that change in length due to thermal expansion is original length alpha del T. Change in temperature and thermal coefficient linear expansion. Okay, so there will be thermal expansion. There will no sigma x because there are no constraint, no stress, thermal stress. It will not be thermally stressed, or there will not be generation of this. There will not be generation of resisting force, and hence no stress in free expansion. But in fully prevented case, what is fully prevented case? Okay, so I was talking about this. Okay, sorry, this is free stress if it is fully prevented like this. Okay, so in this case, we have del L is equals to 0, del L total. Yeah, yeah. Due to thermal stress, I'll know that L del L or del LF is, it has to expand in this length, expand this length, but this length will cause a uh, thermal stress. So what is thermal stress? Value of thermal stress. Okay, I know that L equals to del L equals to PL by A E. So if I pose this here, PL by A E equals to L alpha del T. L will be cancelled. So P upon A is our new stress, which is generated due to thermal reason. So it is thermal stress del TH equals to E goes there. So alpha E del T. This is our thermal stress in fully prevented case. So partially prevented case. So what is partially prevented case? There is a case where, oh sorry, there will be a case, okay, like this. There will be small gap. Suppose X in here. Okay. Then at this case, for this case, this is partially prevented. We are talking about linear stress and okay only, not considering the Poisson's ratio and the lateral strain. Okay, lateral strain or lateral stress. So in case of partially prevented, I have the formula sigma th equals to E is same, uh, but since there is L alpha del T minus X, which is the gap, is divided by L. Okay, so it generates strain. It is the strain, thermal stress, elongation due to thermal length minus this gap upon original length. This is original length, and this creates the strain, which when multiplied with E creates a stress. So, in the fourth case is, it is the case where the consideration of mu or Poisson's ratio is done, where a plate is there and it is prevented, from all direction, uh, partially restricted. Okay, sorry, not all direction. It is a partially restricted in y and free in x. It is free in x. Okay, and y is partially restricted. So in this case, del L of x equals to 1. Okay, sorry, L plus mu. This is L, this is y, and this is x. Y plus mu alpha del t. Okay, this is change in length in x equals to L plus mu alpha delta. So what if there are other cases also? What if what the direction of plate? Sorry. Then what direction? Sigma th. It is prevented. Then our stress will be E alpha delta by 1 minus mu. What direction in plate? Plate. Plate will have two dimensional only, and thermal stress in other direction is sigma t. In case of cube, okay. In case of cube, where what direction are restricted, thermal stress will develop due to the restriction. Of course, we know this. E alpha delta upon 1 minus 2 mu. Due to other two direction, thermal stress in one direction will be this. Due to other one direction, thermal stress in a plate is this. And due to for partially prevented case, not partially prevented, plane restricted in Y. This is restricted in Y. This is restricted in Y, and it is free in X. Free in one direction in X. Okay, free. Okay, I think this is all about the thermal stress and thermal stress, thermal strain prevention. Okay, I think you guys will have a very useful time with these formulas. Okay, thank you guys.